Hi guys, this is your last example for section 7.3. I'm doing number 10D on page 385. And I chose this example because it's a little bit more difficult than the ones you've seen so far in the other videos that you watched, especially with finding the restriction. So the question here, I've written it here, the log of x squared plus 7x plus 12 minus the log of x squared minus 9, and you're asked to simplify and state any restrictions on the variables. It's important to note that even if you were not asked for the restrictions, you still need to find the restrictions automatically for simplifying logarithmic expressions, similar to when you had to automatically find the restrictions when you were simplifying rational expressions. When you learn that in grade 11. Okay, so our first step here would be just to apply the quotient law to make it into the log of 1 quotient, since it's a difference of logs. All right, and now to simplify it further, we can simplify the inside of the log, which is a rational expression itself. And so think back to how you did that. One of the tools that we had there was we could factor and reduce, right? So we're going to factor the numerator. Just a simple trinomial comes to x plus 3 times x plus 4, or the reverse. I said it of the reverse of what I wrote, but same thing. Bottom is a difference of squares, factors to x plus 3x minus 3. Okay, now remember when you simplified rational expressions, we need to make sure that we do the restrictions after we factor but before we reduce, because we don't want to miss any of the restrictions. So we're going to reduce that x plus 3 ultimately, but we need to include that in the restrictions. So let's go ahead and find the restrictions now. And in order to do that, first we're going to get the roots of, in order for this log to be defined, the entire inside expression of the logarithm, the rational expression inside here, needs to be greater than 0, right? Because log of 0 is undefined and log of a negative number is undefined. So we need to figure out what x equals in order for that whole expression to be greater than 0. And if you remember back to, I believe it was chapter 3, when we solved rational inequalities, the answer to that will be intervals of x, not simply multiple values for x, but actual intervals of x. So the best way to do that, again, if you think back to chapter 3, the way we did it there was with an interval chart. So we start by getting the roots of that expression inside the log. And so our roots are -4, -3, and +3. Roots of all of the factors, including the ones that you are crossing out and reducing. And then we make an interval chart. So we need to put our intervals around these values at the top here. So starting with -infinity, then go to -4. Next would be -3. Make sure you go from least to greatest. And then +3. And then to infinity. And then, here, let me fix that infinity. It looks weird. Okay, that's better. And then down the left-hand side, if you recall, we put our factors in the chart. Now, the x plus 3 on the numerator and the denominator are being canceled out. Therefore, whatever sign that x plus 3 would have in the interval chart on the top, it would be the same sign on the bottom. So we don't actually need to include x plus 3 in our interval chart, because let's say, for example, that this factor came out negative in a certain interval, then it would also be negative over here, and they would cancel out anyway. So we don't need to bother doing that. We can just leave that factor out of the interval chart. So we just need to put x plus 4 and x minus 3 in our interval chart. Okay, so now we go ahead and test the intervals. Taking any value between negative infinity and negative 4, we get, let's say, negative 5, we get negative, negative. I'm just going to go through and fill these in. You can figure them out on your own if you like, just to make sure you know how to do it, just to save some time. Okay, and then we need to divide them. So this negative divided by negative is positive, negative, negative, positive. All right, and then we are looking for the positive intervals because we want the entire expression inside the logarithm to be positive so that the logarithm is defined. And so that would be this interval and this interval. So our restrictions here would be that x must be less than negative 4 or x must be greater than 3. Writing that in, oops, I did this before, let me get rid of it. Okay, writing that in interval notation, it would be x has to be an element of negative infinity to negative 4, union 3 to infinity. So those are our restrictions. Let's just go ahead and finish. Sorry, let me go back to black here. Simplifying. So we had the log of x plus 4 times x plus 3 over x plus 3 times x minus 3. And we canceled out the x plus 3s, so we are now left with x plus 4, log of x plus 4 over x minus 3 with those restrictions. Now, if those intervals for restrictions seem a bit strange to you, then you can test them out just to make sure that they work. And so you can do a check where you take any value that is greater than or equal to negative 4. So let's try negative 3, for example, and see whether the logarithmic expression is actually defined. So log of negative 3 plus 4 over negative 3 minus 3 equals log of 1 over negative 6, which is a problem because log is not defined for negative values. Okay. Similarly, you could take any value between negative 4, any value between and including negative 4 to positive 3 and try it out and see that it doesn't work. And if you want to verify that the values in the restriction intervals do work, then take any value in those intervals and try it out, and you'll see that it does work. Let's do one just for fun over here. So let's take x equal to 5, for example, which is in the interval 3 to infinity. So that would be 5 plus 4 over 5 minus 3, which would be log of 9 over 2, which is fine, right? We could get an approximate value for that, but I'm not going to bother. But we know that it's defined because 9 over 2 is greater than 0. And that's the end of this video. Bye!